Hey everyone, welcome back, and today let's solve Leetcode problem 1524, titled Number of Subarrays with an Odd Sum. So we're given an array of integers array, and we want to simply return, like the problem name itself says, the number of subarrays that exist within that input array with an odd sum, or that have an odd sum. And since the answer can be very large, we want to return it modulo or modded by 10 to the 9th power plus 7, which I believe is just a very large prime number. Now, just to kind of clarify and reiterate what odd really means, basically when they say all the number of subarrays with an odd sum, basically their sum has to not be divisible by 2, right? That makes it non-even, or in other words, odd. That's the parity definition of an odd number, if it's not divisible by the integer 2. So in example 1, we have our input array to be 1, 3, 5, and in this case we have 4. Now what does this 4 signify? This 4 basically tells us that we have 4 unique subarrays in this input array that basically, of course, is contiguous because it is an array that has an odd sum. And all of those subarrays, all of those subarrays that do actually have an odd sum would be 1, 3, would be 1, 3, 5, and would be 3, 3, 5, and would be 5. These are all of these subarrays of the input array 1, 3, 5. As you can see, we have, I believe, there is 6 of them. Now, we want all of the subarrays that don't, or rather, that do have odd sums, right? Because that's exactly what the problem tells us. And all the subarrays that would have that would be 1, 4, 9, 3, 8, 5, and the odd sums would be 1, 9, 3, 5, right? These are all of these subarrays of the input array. These are all of the unique, rather I shouldn't say unique, but these are all of the sums for all of the unique subarrays of the input array. Now, of these sums of all the possible subarrays that we could form with our input, which one of these are odd? Well, 1 sure is odd, 4 isn't, 9 sure is odd, 3 sure is odd, 8 isn't, but 5 sure is odd. These are all of the sums of subarrays from our input array nums that are odd, 1, 9, 5, and 3. And so since we have 4 of them, or 4 subarrays with that odd sum that we could possibly form from our input array, the answer would be 4. And these are the subarrays that do so. 1, 1, 3, 5, 3, and 5. And notice how, of course, all singular odd digits or elements in an input array would be considered a subarray themselves, and they would be considered odd as well. In example 2, we have our input array to be 2, 4, 6, and in this case, we can never form any subarray that has an odd sum. Why? Well, because every single element in this input array is even, and we know that any even integer sure is an odd, and any even integer plus another any even integer, it's always going to give us an even output, or an even sum, and we're never going to have an odd sum of any potential subarray of any possible elements from our input array, and so we're going to have an output of 0. And finally, for example 3, this may seem a little bit redundant now. We have an output of 16. There are 16 subarrays that have a odd sum. So now let's go ahead and get into the problem solution and how we can kind of solve this problem efficiently. And that kind of leads us to the important observation to really make from this problem, right? And that is that an odd sum has basically 2 different results, or 2 different ways to be able to form, right? Basically, they can be an odd length subarray with an odd sum, or they can be an even length subarray. And if it is an even length subarray, their prefix sum difference has to be an odd sum, because we just discussed that an odd plus an even number is different from an even plus an even number. Any even plus even number is always going to give us an odd number, or rather an even number. But any even plus odd number is always going to give us an odd number. Right? That's very important to note for the context of this problem, right? And so instead of actually checking every single possible subarray, that would kind of be the naive way to solve this problem using nested loops, go literally with every single possible subarray sum, which would be the go of n squared. And instead of doing that, we can actually use something called the prefix sum and use those prefix sum properties to leverage a more efficient solution with those prefix sums to determine how many different odd and even length subarrays we have, whose prefix sum differences actually do result in that desired odd sum. Right? So now let's go ahead and get into the kind of high-level rundown of how our solution is actually going to work, right? We're going to use something called a prefix sum count technique, right? Basically, it's going to be accumulative, and the way that would work is basically we'd maintain 2 counts, right? We'd have the count of the even prefix sums, and we'd have the count of course, the odd prefix sums. And as we actually iterate through the input array, we'd update that running or accumulative prefix sums of all the elements so far. And if the current prefix sum, if it's odd, that means we have actually found a subarray that ends at this current index, or that ends at this iteration with an odd sum. And we want to then count how many previous even sums that we've actually seen before actually reaching this index, because removing them would still yield an odd sum, because an odd sum or an odd integer minus an even sum or an even integer is going to result in an odd sum, right? And similarly, if the prefix sum would be even, same logic, we'd count how many previous odd sums have appeared, because even an even minus odd sum is still going to give us an odd sum, right? And that's kind of how this solution is going to work, right? So we're going to have an odd count to track how many times we actually see an odd prefix sum, an even count how many times we've seen an even prefix sum, a prefix sum as a whole. That's the cumulative sum of all the elements so far without removing any prefixes, and that we're going to have a result which stores the total count of the entire input array subarrays that have an odd sum. That is going to be an effective result. That's what we're going to return. So now let's go ahead and get into the code of the solution. Now, not related to the solution directly or the logic behind this approach, I'm just going to first initialize my mod, right? It's going to be 10 to the 9th power plus 7. I'm only really doing this because the problem tells us to. The answer could be very large, and so to avoid any integer overflow or anything like that, we have to return it modded by this large prime number, right? Now, really not related to the solution here. That's just because the problem statement tells us that, and we want to avoid integer inflow. Now, let's go ahead and get into the initialization of all the integers that we want, the cumulative sum, the odd and even sums, and the result, right? So as we talked about just now, we'll get those values, prefix sum and odd count. They're both going to be initialized to 0. Now, I don't remember if we need two zeros here. I'm going to assume that we do, or in fact, I might just bring them down in 2 lines. I think that's a little bit easier and for me to understand as well. And we're also going to get an even count, the kind of counterpart of the odd count. It's going to be initialized to 1. All right, more on that later. And then we're going to have a result equalized to 0, right? This result is basically how many sums or how many subarrays that we actually found in the input array that have an odd sum. Now, something that you may have noticed in this initialization, we initialize the odd count, basically the number of times that we see an odd prefix sum, to be 0. However, the even count would start as 1. Why are we starting at 1 for the even count? Well, that leads us to another very important observation, right? There's always at first going to initially be one even prefix sum. That would basically be the sum of 0, which means 0 elements without even iterating through the array, just having nothing. And 0, last time I checked, was indeed an even prefix sum, right? And so we do have to actually start with 1, because we do consider that initial sum 0 to be even before we even start iterating through the array. Right? Now, to kind of reiterate what these elements or these integers actually do, prefix sum is basically going to track the number or the accumulative sum, running sum, if you will, of all the elements so far, and the odd count and the even count would track the number of odd and even prefix sums that we've actually seen before, and the result is simply going to show the total number of subarrays with that odd sum that we actually build up as we iterate through the array, and that we actually use the prefix sum to compute, and effectively the value that we're going to return, because that is exactly what the problem wants us to return. Now, let's go ahead and start iterating through the array. So for every single number or num in the input array, so in array, that's what they call it in the context of this problem, we're first going to update our accumulative sum. So prefix sum plus equals the current value, num, right? Basically, it's the accumulative sum, and we're going to process each element one by one and update the prefix sum by adding the current number. Now, what if the current prefix sum after adding this element so far, what if it's even? Now, how do we check if it's even? Well, if its value modded by 2 is equal to 0, meaning it is actually divisible by 2. If it is, we know it is defined to be an even number. So if the prefix sum is even, we then want to add to our result the odd count, and then we want to set or increment our even count by 1. Now, how does this really work? This is the prefix sum logic part of this solution, right? We're adding the odd count to the result because any subarray that ends here with an odd prefix sum before it will still contribute to a valid subarray, because we can still remove it and expect an odd sum, because an even sum minus an odd sum would still give us an odd sum, and we want the odd sums, and so we're going to add the number of odd sums, odd prefix sums that is, up until this index that we've seen so far. And then we have to actually increase the even count, because of course now we know we have another even prefix sum at this iteration if the current prefix sum is actually divisible by 2, meaning it is actually even in this iteration. Now, what if it's not divisible by 2? What if the current prefix sum is odd? In that case, we want to increment to our result, you guessed it, the even count, and then increment the odd count by 1, because we've seen one more prefix sum that has an odd value, right? And we're adding even count to the result this time because removing any previous even prefix sums that we've seen so far would still yield an odd sum, because any odd sum minus any even sum, it's still going to give us an odd sum. We want odd sums, and so we're going to remove all the odd prefix sums subarrays that we've seen so far up until this iteration. That's the prefix sum logic of this portion. Now, again, pretty unrelated to the solution here. At every iteration, we want to actually mod our result by the mod integer, or by 10 to the 9th power plus 1. Again, we do this every iteration to avoid integer overflow. And once we actually iterate through all the elements and get all of the odd and even prefix sums and subtract them accordingly with the current accumulative sum, we return the result, right? That would contain the total count of the subarrays with the odd sums. And so unless I made any syntax errors here, this should be accepted and there should be a valid solution. And as you can see, this really is just about as efficient as you can get it to be. Now, on a high-level rundown, how can we kind of define our solution? Basically, we traverse the array once, it is a one-pass solution, and we update our prefix sum or our accumulative sum as we actually go. And then we actually count how many times we've seen the odd and even prefix sums, or frequencies, if you will. And if the current prefix sum or accumulative sum, if it's even, we know that all these subarrays that ending here that were preceded by an odd prefix sum would be counted, because we can still remove an odd prefix sum from an even prefix sum and get an odd value. And if the prefix sum currently is odd, then all the subarrays ending here that were preceded by an even prefix sum would still be counted, because an even prefix sum minus an odd prefix sum, or an odd prefix sum minus an even prefix sum, is still going to give us an odd value. And then we simply return the total count of the subarrays that we added to the result with an odd sum modded by 10 to the 9th power, right? Or rather, 10 to the 9th power plus 7. So for the runtime complexity here, it is a one-pass, single iteration solution with one for loop here. We iterate through every single element exactly once, and so it is going to be a big O of n or linear time solution. And the memory complexity, believe it or not, is actually constant. It is actually big O of 1. Because we're not actually using any auxiliary memory or any extra data structures. We really only are using a few integer variables like prefix sum, odd count, even count, and result, and they are not going to grow linearly with the input size. They're going to be constant. They're going to be big O of 1. These are simply just integers that we define in a solution. So if you guys enjoyed this solution and learned something new, please consider liking this video and subscribing to my channel. And without further ado, I'll see you guys in the next video. Bye bye.